almost always when we're working with partial derivatives, it's going to be easier to just take the function as given, however many variables it has, and just mentally think of all but one of the input variables as being a constant. Okay. But we do need to remember the definition of a partial derivative. It is the derivative of a function we get of one variable when we hold the other one's constant. And sometimes we don't have the option of just thinking of one of the variables as constant. Sometimes we actually do need to fall back on that definition and plug in the specific constant first. So I've got a rather interesting function here. This is a piecewise function of two variables. F of xy is 0 if x is less than or equal to 0, or y is less than or equal to 0. And an or is always interpreted, unless otherwise specified, as an inclusive or. So if either x or y is 0 or negative, or if they both are, we're going to get 0. We're going to get 1 if x and y are both positive. This is an and here. So if I think about that, if here's the xy plane, on the axes, of course, one of the variables is going to be 0. So the axes are going to map to 0. Quadrant 1 is the only quadrant where both x and y are positive. So points that are in quadrant 1, but not on the boundaries of it, are going to map to 1. In quadrant 2, x is negative. In quadrant 3, both x and y are. And in quadrant 4, y is negative. So points in these three quadrants and points on the axes will map to 0. So I happen to have a copy of the xy plane here. I like this copy. It's a pretty shade of blue. Okay. So you can see you've sort of got the x-axis coming out towards you, and the y-axis is the one that's coming this way. The z-axis would be sticking straight up. So this is quadrant 1, right? Because x is positive and y is positive. This is what the graph of that function would look like. Quadrants 2, 3, and 4 would be on the xy plane. Points that are strictly inside of quadrant 1 would jump up to a point of 1. So we can see this is a function that is clearly not continuous along the boundaries of quadrant 1. Anywhere on the positive x or the positive y-axis, and certainly at the origin where they meet, this function is not continuous. Surprisingly, both partial derivatives are going to exist at the origin, and in fact at all points along the x and the y-axis. And so this example is going to show us two really important things. First of all, that sometimes we do have to fall back on the definition and actually plug in the number for the variable that we're holding constant. And second, that existence of the partial derivatives is not enough for a function to be differentiable. Now, we haven't talked about what it means for a function of two variables to be differentiable, but if it's not even continuous, I think we can feel pretty confident that it's not going to be differentiable. And that's the case. If it's not continuous, it's not differentiable. So the existence of the partial derivatives, I guess the whole is more than the sum of the parts, because the two partials existing is not going to be enough for us to say that this function is differentiable at the origin. But let's see if we can't go ahead and find these partial derivatives. Okay. So the partial with respect to x, that's going to be the full derivative with respect to x of f of x comma 0. I'm going to hold y constant at 0, okay? Because we're evaluating this at the origin, okay? Now, if y is 0, that automatically makes the function value 0. So this is the derivative with respect to x of 0, but the derivative of any constant is going to be 0. Okay, so it doesn't matter that I'm evaluating it when x is also 0. As long as y is 0, my function f is the constant function 0. Okay. All right, f sub y at the origin. That's going to be the full derivative with respect to y of the function we get by holding x constant at 0 and letting y be our variable. But once x is 0, my function is 0. So we're taking the derivative of a constant. That's because if we take a look, I don't care what's happening in quadrant 1, because if I'm holding y constant at 0 so that I'm not moving left or right, I'm going to be on this x-axis here, and this x-axis, the curve of intersection I'm getting, is just the x-axis. It maps always to 0. I'm getting that constant line. Same thing when I hold x constant at 0 so that I'm on the y-axis. The y-axis was on the part of the graph that just stays on the xy plane. So the curve of intersection that we're getting is just that line, just that y-axis. Okay. So both partials exist and are 0 at the origin, where this function does this crazy sort of a jump. Kind of interesting, but recognize if you have something like this, if you have a piecewise function, you may not be able to just work with the formula that you're given because you've got two different formulas. Now, obviously, if I were taking the partial derivative at a point like 1, 2, that's in the middle of quadrant 1, then I could just say, oh, so I'm working with this formula. Okay. But if I'm taking a derivative at some point on this boundary where the function changes, I need to actually plug in the constant value that I have in order to create this function of one variable that's what I'm working with.